welcome. Thank you very much for making some time to join us today. I'm quite excited to talk about this. This is our second conversation about transformers manufacturing in the commercial industrial space. And so we'll be looking at, in some aspects the same, some aspects different. But before we do get started, let's just talk about some basic rules. Everybody that is a participant should be placed on mute. You won't be able to talk through the presentation. Somewhat unfortunate about these options, but that's the way it is. Please do ask your questions though in chat, and at the end of the session we'll answer as many as we can. But what I like to do is I like to go back, and all those that we couldn't answer, we'll answer the questions, and the Q&A will go out with the slides. The presentation and the recording will be shared with you, and nobody leaves one of our H2 scan presentations empty-handed. You will receive a white paper that will also talk a little bit about cost justifying this and how you can go about making transformer monitoring viable within your organization. And as always, we have a huge amount of additional information in our resource center. Throughout the presentation, there's a number of hyperlinks. When you receive them, you'll be able to click on it. But if you go to our website and go to Resource Center, you'll be able to filter and look for information that's useful and specific to you. So why are we here? If you look to the left, this word cloud has got a significant number of industries. There's food, there's shipping, there's airports, there's rail, there's semiconductor, there's all sorts of manufacturing and glassworks. In short, if you work in any of those industries, you probably own or operate or maintain your own transformers, or you operate and maintain transformers on somebody else's behalf. And as we go through today, what we really want to examine is that increasing trend. If you can't turn on the news or go to an online outlet without reading about yet another transformer failure, so we'll look at some of that. We'll spend a little more time talking about the complexities of what failures cost your business and why that matters. But really, at the end of the day, the most important thing is to talk about is how we avoid unforeseen transformer-related outages. And then, of course, no webinar would be complete without a word from our sponsor, and we'll spend a few minutes just talking about how we can help our business partners solve those problems. So I said it earlier, you can't open a magazine, you can't open a digital outlet, you can't move LinkedIn without reading about yet another transformer failure. And of course, there's no transformer failure that is more topical today than the transformer failure that shut down Heathrow Airport quite recently. I believe it cost the UK economy £50 million or $56 million. And that's really what we know of. I think there's a lot more complication, a lot more expenses and other complications associated with it. But it probably is the quintessential failure that nobody wants to be associated with. But they're not alone. Delta had a 5-hour power outage in an operations center that cost them 2,000 cancelled flights and about $150 million loss in revenue. And if you're on the rail, if you take rail, if you operate a rail system, they're the hardest hit, in my opinion, because not a month goes by without us reading about the commuters and how they're significantly inconvenienced. And I think just last year we had a failure in the New York City subway where people were stranded, some in the tunnels for up to 2 hours in complete chaos. And I just have to go back as far as last month to find another one in Long Island where a transformer failure in the tunnel disrupted the service and actually injured people. Like, why limit ourselves? Transformer failures have disrupted water supplies in Houston for nearly 2 days. And if you read through some of the articles, you'll see that if you operate transmission-based transformers, if you operate 400, 500 plus MVA type transformers, industries put a lot of energy into trying to understand how to make them secure, how to make them reliable. But I think people are starting to understand that smaller transformers and the size of the transformers that you own and operate are for the large part still yet somewhat unaddressed. And so that's really a little bit about what we're going to try to cover today. I picked on a few of the more prolific events, those that make the media, those that social media have taken to a bit of a feeding frenzy, perhaps in some cases. I could spend an hour just talking about that, but we don't really want to make everybody really disheartened. At the end of the day, I think what's important to understand is that there's no one industry, there's no one application, and there's no one use case that this applies to. This applies to transformers across the board, whether you're a small industrial entity, whether you're a large utility. At the end of the day, smaller transformers and their reliability are becoming more and more of a challenge for the owners and operators of those assets. I spend a lot of time talking to people about their transformers, and in fact, this presentation, in more cases than one, I'm going to sort of talk about the things I hear, the things people say to me. But the three things that I hear most common is, we can't afford it. DGA monitors are too expensive. And we'll talk about some of these terms in a short bit. Or we can't justify it to management. We can't get an economic motivation for it. Or the one that probably irks me the most is our transformer failure rates are not really that high. I mean, that one really gets to me. And I'm thinking to myself, how Madison, what they would have said the day before that fire on the right, and what they would have said the day after that fire on the right. And I don't know those people, I haven't talked to them, but there's enough people that I have spoken to that feel this, and they would feel that and continue to feel it until they have that fire that you see on the right. My response to everybody on this call, to people I talk to, is, why would the loss of even one preventable transformer failure be acceptable to anybody? We saw the failure in Long Island. 4 people injured. They were lucky that it was just injuries and not something more severe. So as we talk today, the objective is, we can't prevent and predict every single transformer failure. We're going to focus in on a specific set of them, but we are going to focus on the preventable transformer failures and how we can take advantage of the technologies that are available to us to achieve that. So I said, one of the most common things is our transformer failure rates are not high. And I hear it. I've probably heard it from 95 to 99% of the people I've spoken to. And the truth is, it's more frequent than you realize. I went to the internet because, they know everything on the internet. And I found a few key articles. The one on the right from Jeffrey Reitz, I don't know him, but I found his article and it was really insightful reading. Because the automated news data will find that a power transformer fire or an explosion occurs every 7 to 10 days. Now, that's not a transformer failure. That's a fire or explosion. That's the one that is spectacular. That's the one that draws a lot of publicity. But smaller incidents happen multiple times daily. And as I researched a little further, I found the liquid-filled transformer failure rates are 0.4% per year per IEEE 493. But that's only good as populations approach 20 years. After that, it goes up exponentially. And the net result is, based on our current populations, you'll find that in developed countries, about 2 to 3% of our transformer population will fail. And in 12 to 17% of the population will fail in developing countries, but largely due to the age of their installed base. So when we say our failure rates are not high, they are actually quite high, and they may not feel that because you haven't seen anything catastrophic. But with these statistics, it's a matter of time before it catches up with at least somebody on this call. So, okay, they fail. I think the single biggest question is, what does it cost you? What does it cost your company? What does it cost your enterprise if a transformer fails? Now, I can find you as many answers as I can type studies. So I've picked a few that I thought were really interesting. The EPRI, the Electricity Power Reliability Group, they did a study, and I really do trust the work they do. They estimate that a power outage will cost $16,000 to $35,000 an hour, and that's an average. And that doesn't take into account a lot of consequential losses. If you're a semiconductor manufacturer, this clearly doesn't even fall into cover the cost of a single wafer. But $16,000, if you're down for a day, a week, a month, what does it cost you? It's a significant cost for your organization, both at direct and secondary costs, the impact on your manufacturing facility. In a very significant and large survey, I think 1,450 companies were interviewed, and 82% of them said they saw a downtime cost of $260,000 per hour as an average. And a VIA study said it's $138,000 to $540,000 per hour. Now we're looking very much more into the consequential, or the cost of an outage, and what it not only is the direct cost of replacing the transformer and all the equipment, but what it may cost you in lost revenue. Gartner put it at 336. And Poneman Institute took it as high as 540. Actually, when you receive the presentation, there's one more slide that I'm not going to go through, which really breaks it down by industry. And it's no surprise to see that the industry that has over $500 million an hour, that is in the high-speed brokerage. But that's a bit of an exception. But losing a single transformer can be particularly expensive for some industries, as you'll see. So these numbers, pick one, but they are an extremely compelling business case for the most demanding CFO. There's no CFO who won't look at these numbers and say, it really does make sense for us to try and eliminate just one. If we eliminate just one preventable transformer failure, we've succeeded in doing something good for our business. And so I'd encourage you to look. If you can click on links as you get this, when you get this information, and you'll be able to pull a lot of the information that you need to create a compelling business case to justify this. So that's the background. But let's just talk a little bit about a transformer failure, because everything I've shown you is the one on the left. When transformers fail, occasionally, they are catastrophic, and they are made all the more catastrophic by social media and by everybody playing it over and over and finding 12 different ways to play it over. The Heathrow fire, I think, cost the UK economy £50 million, but their media probably made another £50 million in just writing about it. So I think they broke out even. But the truth is, it's sometimes catastrophic. Sometimes they just plain rupture. They leak insulating liquids. And sometimes please forgive me if I call it oil. I'm somewhat in the old school. So if you hear me talk about oil, I mean the insulating liquids of the various forms. But more often than not, you couldn't tell. You can stand next to that transformer. It'll look as good as it did the day you installed it, and you wouldn't know that it's failed. They are not always as catastrophic. They are not always as spectacular. And in fact, another article I found, I was reading it, and I just was so drawn by how well Neil Probert, I don't really know him, I hope I pronounced his name well, how well he put it. He just said, transformers don't fail overnight. They fail gradually, and they fail silently. And most transformer failures just aren't sudden. They're the result of a very slow, and more importantly, invisible process inside the main tank that we call degradation. So when transformers fail, again, specific to this, they fail slowly, they fail silently. But when they fail, it is invariably, it's almost always very expensive. It's almost always very, very inconvenient to your business. It could be that if your organization, your production facility, your company is under the public spotlight, it's invariably a public relations challenge. Think about an airport, think about commuters on rail, think about if you're just being watched, if you're in aerospace and somebody sees something, the media gets a hold of it. It is a public relations challenge for so many of us. They are always costly to mitigate. And even more so if there's a fire or an oil spill. Those days of us just pouring sand over a large oil spill and moving along are gone. And there's a lot of cleanup costs. But most importantly, and I think we're all very familiar with this, unless you were already planning to replace a transformer and the delivery of the new one is imminent, they can take a year to replace. If you go off-brand, perhaps you can get something a little bit sooner if you import it and you're off-brand, but your risk associated with an off-brand transformer might not be the same. The biggest problem, the single most important point about this is, set all the topics above aside, When transformers fail, it is almost always unforeseen. Almost always. Nobody sees it coming. In a significant survey, over 97% of the people surveyed said they had no idea that transformer was failing internally. They had no idea there was a problem, and they did not foresee that transformer failing when it did and how it did. So going back to Neil Probert's article, he talks about the two most overlooked threats in a transformer. Remember, he said that they fail overnight, they do fail slowly, they do fail silently. And the two most overlooked threats are unmonitored transformer behavior and unmonitored incoming supply disturbances. Now, we'll talk more about the top one, the transformer monitoring. The unmonitored incoming supply disturbances, perhaps through faults, or if you've got some grid disturbances or something that pass through the transformer very quickly and cause damage very quickly. That's not really within the monitoring realm. There's not much, you can't do anything about that unless your protection relaying separates that transformer from the fault quickly enough. We can't change that for you too easily, outside of harmonics, of course. But we're going to focus the rest of the conversation on monitoring. The biggest threat you have is if your transformer is not monitored. And before I do, I said I'm going to talk a little bit about the way monitoring fits in. I speak to a lot of people, and I'll tell you that one of the most common questions is, we don't need to monitor hydrogen. We've got a Buchholz. Buchholz monitors gas for us. And in fact, yes, Buchholz relays, for those of you who are familiar with them, they pick up a rapid rise in pressure. They're a protection relaying device that will just measure purely rapid gas production and will trip the transformer out. They aren't concerned about anything slow, and they aren't concerned about concentrations. It's simply a volume play. Protection relaying, the purpose of that is to simply isolate that asset from a fault or from a source of energy fast, really fast. Under 20 to 60 milliseconds, and every time I read more about the new relays, they're getting even quicker than that. But at the end of the day, protection relaying isn't monitoring. A Buchholz relay is a protection relay. It's intended to detect an internal and very rapid fault. So it's not the same. I've also heard people say, well, we got SCADA, we monitor our transformers. Yes, you monitor your transformers for operational visibility and control within the context of what the transformer is supposed to do and the grid needs. The time frame for that, yes, it can be longer. I'm talking about the age of data. The data that you see at a SCADA center is typically 1 second old, 4 seconds, sometimes a little longer, sometimes a little shorter, but for the large part, SCADA is simply about ensuring that the asset is performing within the needs of the grid, meeting the load meeting the load demand, and ensuring that it's connected where it's connected and that your load flows are well balanced. It's not monitoring. In fact, many SCADA systems will discard data once they've been viewed if they aren't in an abnormal state. So there is really very little monitoring in the traditional context. Asset monitoring is what we're talking about today. And it's by my definition, I apologize, the continuous observation and analysis of the operational condition of the asset, of the transformer in our case, to detect early signs of wear, of degradation and impending failure. And the time scales for monitoring, it's days, it's weeks, it's months, even longer. We're not in the second realm. We're not in the millisecond realm. We're not even in the hour realm. When we're looking at monitoring, it's the continuous, that's a key word, observation of the condition of the asset with a specific intent to detect early signs of wear, degradation. I think one of the terms we use for early faults, we call them incipient faults. The purpose is to catch an incipient fault before it gets continuously worse and damages the transformer beyond an economic repair. Inspection is a bit of a loose word, so I've introduced it. This is the discrete or periodic measurement of key condition indicators, such as dissolved gas. You may do dielectric strengths. The time scale is typically once a year, once every 2, 3, or 4 years. Sometimes there's period. If any of you are on the call are from industrial organizations, you probably are taking annual maintenance shutdowns or biannual maintenance shutdowns. This is when you might do it. If you're going and drawing an oil sample to get the dissolved gas status, that's this information. But you'll see how it's different from monitoring. Is it's discrete, it's periodic, and the time scale is typically, on average, the time scale is usually annual, never shorter. Not all, there are a few exceptions, but for the large part. So as we talk through some of these aspects, we really are going to talk about asset monitoring, and in the context of an inspection, perhaps the dissolved gas. So that's really the realm we're in. We're not concerned about the other two, but I put this in here so that we eliminate any confusion, because as I speak to more people, I see there is some differentiate. People are not always clear on the difference between SCADA and monitoring or protection. So we're going to monitor our transformer. We're ready. We're off to the races. We're at the start line. The starter shoots the gun, and we're ready to go. And then we realize that the most expensive asset in our substation on our grid, the transformer, has no self-diagnostics. They are, for the large part, not digitized. They're almost always analog. And as we go to the front of them, we'll see some oil level indicators. We'll see some temperature gauges. Yes, they may be digitized, but they are simply digitized with the intent of feeding them perhaps into a cooling system, perhaps more than likely into SCADA and protection relaying, perhaps. Transformers are inspected, usually externally, but if you're in that industrial realm where you take your annual outage and you are doing some dielectric strength testing, or you are doing some DGAs and things, partially internally, perhaps every 4 years, you're doing a full electric test suite. So you do have the advantage. If you're usually industrial entities have the advantage of taking their transformers offline for maintenance. So you have the ability to do that. If you're here and you work for a utility, you know that's more difficult. But they are inspected, but that's certainly not monitored. And they're very rarely serviced. So you don't actually know what's going on inside in most cases. So you're ready to go, and this is what you got to work with. And so you start asking yourself, well, how do I get to monitoring? How do I find out what's really going on in my transformer? What's the condition of my transformer with these few tools that I have, as this device came to me from the manufacturer, or came to me from the manufacturer 20 years ago? So to predict to understand the whole concept of transformer monitoring within the main tank, to understand what it is, we have to describe sort of the process that we go through. For those of you who did participate in the last webinar, there is a lot of repetition in this section. I do apologize. But for people that are new, we really wanted you to be able to understand the process we go through, rather than just we jump into, we make a hydrogen monitor. So let's talk a little bit about what that looks like. So we have a transformer. We walk up to the transformer, but for those of you who've been in the industry, I'm told you can listen to a hum and know if it's good. But for the rest of us, we listen, it's humming. We look at the oil level indicator, oil's good. We look at the temperature. Yep, it's all good. But inside that transformer, unbeknownst to us, is the onset of what I call a transformer fault. And I use the word transformer fault to indicate something happening inside your transformer. And I use the word transformer fault to separate it from a grid fault. And more often than not, when we talk about faults, if you come from the utility world, we're normally thinking of a line fault, a busbar fault, or some other fault. We're specifically talking about something happening inside the main tank. That fault, it might be a partial discharge, it might evolve to something, but it starts off probably small, and it creates heat right at the point of the fault. I've read articles where they say that the heat generated by an arc, for example, is as hot as the surface of the sun. But it's very short, it's very brief, and it's very localized. But that heat will cause the oil, the insulating liquids, to break down. As that liquid breaks down, it will result in gas generation, and hydrogen will be the first gas that will get generated, because it's the gas that's generated at the lowest fault temperature. So to say it again, the fault will create heat. The heat will cause the insulating liquid to break down. The breakdown of the insulating liquid will release gases. Hydrogen is the first gas. And hydrogen is one of my chemistry PhDs in the company told me hydrogen is the smallest compound and it's the fastest compound known to man. And I said, nope, he doesn't clearly have a 2-year-old child. But after 2-year-old children, they are the fastest compound. They move extremely quickly. They don't need oil to be circulating in the transformer. That hydrogen will dissolve into the oil and it'll spread modestly, evenly through the transformer, and the concentration of the oil will reach a steady state equilibrium fairly quickly. So hydrogen is the first fault gas generated, and it's one of the reasons we call it the key gas. Some people call it fault gas, first fault gas, first gas. Hydrogen will be generated for all internal failures. So from the lowest temperature type fault to the highest temperature type fault. And then as the fault or the failure progresses, other gases such as methane and eventually acetylene will be generated. And the IEEE C57 104, there's a picture on the right. It will sort of show you how the different gases are generated as the fault progresses, as the temperature goes up. So we have these different gases will be generated as the fault continues. And I know it's always confusing in the new standard to understand the hydrogen, but what you also notice is that the hydrogen concentration continues to grow as the fault grows. So I'll say it again, just to recap. The internal transformer fault will generate heat. The heat will cause the insulating liquids to break down. The insulating liquids will generate gas, and the types and quantities of gas that are generated will depend on the temperature of the fault. So if we're measuring gas concentration, we'll know when the transformer has become compromised, and we'll know I use the word pretty quickly, not real time. We're not SCADA, we're not protection, but we'll know pretty quickly, within hours or within a day, depending on how we've set up our monitoring. We'll know that the transformers become compromised. And of course, if we know all the gas concentrations, we'll know what caused the fault, what the nature of the fault was. So how have we managed this? And this is probably the world everybody's very familiar with. The industry norm is, we all know we've got to do that. We all know we've got to go to the transformers. We've got to go and pull an oil sample. We go take a syringe, we draw an oil sample, we send it to the lab. The lab will do a dissolved gas analysis, or DGA, and they'll send us back the results with all the different gases and the moisture and everything. That's how we get to know what's going on in our transformer. And in addition to that, larger transformers will have what we call continuous multi-gas monitors installed. So you don't have to draw a sample, you don't have to send it to a lab. You put on a multi-gas monitor, and it's a great tool because it's going to, in sort of a modest real time, going to calculate and report back to you the concentrations of all the different gases that are in your transformer. The truth is, these are expensive. They are not cheap. Some of them require a fair amount of maintenance, some less. But because of their cost, it's really difficult to put them onto smaller transformers. So they really are installed, and I use the word transmission transformers. That could come to sub-transmission. Every utility will have sort of different criteria, but they are not installed as widely as people would like. They're not installed as widely as an asset owner would like, or as a manufacturer of multi-gas monitors. Smaller transformers, the orphans in the family, they generally don't have continuous monitoring. They rely on periodic oil sampling and then the subsequent lab-based dissolved gas analysis. So if you're a bigger transformer, you probably know what's going on, especially if it's a critical asset, especially if it's probably sitting under NERC's observation. But if it's a smaller transformer, you're limited to the frequency and the timing of getting a manual sample. And if you remember one of the slides I spoke about earlier, there's this general consensus that industry solved the problem for very large power transformers, always close to solving it. But that smaller transformers generally are forgotten about. They haven't been addressed. And all those failures I showed you in the beginning, and a high percentage of the failures we see impacting commercial and industrial customers, are generally small transformers. Even the transformer at Heathrow, yes, it was a transmission, but it wasn't one of the biggest ones they've got. So by and large, The transformers are a lot of the failures. Look at all the rail failures. They are all extremely small transformers. So they are generally left unattended. So is manual oil sampling good enough? I mean, for heaven's sake, we've been doing it for, I don't know. I don't actually know how long, perhaps 30, 50 years. I probably should Google that and see. But we've been doing it for a very long time. And it's always been good enough, hasn't it? Although I maintain that if it is good enough, why are we still seeing such a high number of failures that were preventable? Manual sampling for lab dissolved gas analysis usually occurs every 1, 2, 3, or 4 years. A lot of people we speak to simply don't do it. They don't have the resources. They don't get down to it. There's always a higher priority. There's always a bigger dragon to slay. So sometimes it just doesn't get done. Or even better still, a lot of utilities I speak to run their distribution transformers to failure intentionally, but that isn't working out too well for them, because unless they're very small, unless they're sort of LV, but if they're MV, medium voltage transformers are harder to source, they take long, and people and assets are getting destroyed, getting damaged. So the other problem with the dissolved gas analysis, remember we spoke about inspection. It's an inspection, and it's a static measure. So it's a one-time measure of a combustible gas at the time the sample was taken, assuming you did it well. I've spoken to a few people who've said their biggest problem with the manual sampling in their case, and we assume it's not ubiquitous, is that there's a lot of human error in drawing samples and getting them to the lab. And we've even heard cases of labs making mistakes and putting oil into contaminated beakers. So, but assuming we got all that right, it's a one-time snapshot. If I went to somebody and I said their standing heart rate is 40, is that useful? In isolation, I don't think it's very useful. If you're talking about a marathon runner, then, well, there's nothing wrong. Perfect. It makes sense. But if you're talking about somebody else, wow, that might be a little bit low. Might be time to get to a doctor and figure out what's going on. So without context, you don't know how to interpret the data. It's a discrete sample, and therefore you don't know what action to take. And I'm going to thank Delta X Research for this information and for the ability to use it. Delta X Research has a plethora. They have so much historic data, and they do a significant amount of analysis on the data. That's part of the service they sell and deliver to customers. And they've observed empirically that a transformer fault will migrate from gassing to failure in less than 6 months. If you're doing an annual sample, there's a 50% chance you can miss that event. You can go from the first signs of gas through to a complete failure and not even know about it, and you'll shake your head and say, "Wow, what happened? We just took a sample and we didn't see this." The reason is that that period is statistically at 6 months and shrinking because of the way of the nature of the load patterns, the amount of load we put through the bidirectional loads and every other aspect of our grid that we didn't plan for when we planned a vertically integrated grid. So we spoke about a discrete sample. Let me show you what context looks like. And context comes from what we call continuous monitoring. So knowing what the gases levels look like over a period of time provides context. Many people have said to me, "I don't want to do any single gas monitoring. I don't want to do hydrogen monitoring. I don't want to roll a truck because every time I see hydrogen, because all transformers have hydrogen," which is true. It's not uncommon to get to a transformer and find there's some hydrogen. And, well, clearly you don't want to roll a truck just because it's there. The most important thing to do is to know is what's the context. So let's look at the very first one. This particular customer, they saw this rapid rise in gas. Okay, it didn't go very high, but it was still very rapid. And in our world, we do like to look not only at the level of the hydrogen, we like to look at the rate of change. And so the first response was, "Wow, this is quick. This rate of change is high." And there was an initial concern. And as they were getting ready to go and draw a manual sample and get it analyzed to see if they could figure out what was happening beyond that, they noticed that the gas level stabilized and very quickly dropped back to zero. They went to look beyond that. They went and had a look at the grid logs, And they found that there'd been an earth fault. One of the conductors had fallen to ground on a line feeding the substation. That had generated a through fault, and the through fault it caused the heating in the transformer. The heating had created clearly the gas. And so the transformer itself didn't have a fault. There wasn't an incipient fault. It was simply a momentary heating caused by that through fault. It's good to know about it. But the fact that it then dropped back to zero and went off back to zero, the operator, the owner of that transformer could say, okay, no further action required, no truck to roll. And they understood that this is very typical of a through fault. They've recorded that through fault. Another important thing is just to see how sensitive monitors are today. We picked up this 2 ppm production, and then it dropped off very quickly. So that's a use case. It's a classic use case of a through fault, and it saved the operator from having to overreact. It saved the operator from having to roll a truck, and they were able to process, analyze their context, and they moved on. The second one, 8,000 ppm. Really alarming. When they first saw this, they were ready to go and drain the transformer and have a look at it. But in point of fact, as you look at it in the context, what you see a lot of up-down. That's the diurnal effect. If you were to break it down and look at the timelines, in the day it went up, in the night it dropped. But if you took the average, it was pretty stable. It was actually not generating significantly more over a period of time. Looked a little bit further, and they found that this transformer was in the presence of a significant amount of harmonics because it was directly located onto a solar and wind farm. We know the inverters are generating a lot of harmonics. The harmonics are causing heating in the transformer, those circulating currents. And in point of fact, during the day, we had more harmonics as the inverters were working. In the night, everything cooled. We had fewer harmonics, and this gas was able to subside and as the transformer temperature dropped. So knowing context, looking at the thing, at the performance, we were able to say, look, the gas level is modestly steady. Keep an eye on it. You still got to watch it because this is still very high. And I think the customer picked 10,000 ppm. They said when they get to 10,000 ppm, they're going to go and they're going to degas this transformer because they have a lot of transformers with these large gas levels. So no truck to roll, put it on watch, and they would pay close attention to this transformer. The third one, it was really interesting. On the flat line, this customer did a manual oil sample and everything was normal. Everything was 100% clear. And then suddenly there was this rapid rise in hydrogen. I always make fun of the situation. The first thing the customer did was call us and tell us that our sensor was broken. But once we'd analyzed the log file and assured them that there was hydrogen, they then went and took a manual oil sample as we recommended, because at this point, we got a modestly and rapid rate of hydrogen production. It's not dropping off. It's sustained. And this transformer wasn't even on load. It was just energized. And we recommended an immediate manual DGA, and they found a lot of acetylene. And this pattern is very typical of a main tank fault onset. The transformer itself couldn't be saved because of some rust damage. There was a lot of rust damage that had taken place, which caused the arcing, which caused the rapid production and acetylene. But had this transformer been loaded in its current condition, it is quite possible that somebody could have been injured. This certainly would have had a lot of damage, material damage and asset damage, had they put this transformer under load. And bear in mind, they had, just before they energized it, taken a manual sample to ensure that everything was normal. So what are we saying? Short version, if we monitor gas generation and hydrogen in particular, it is a leading indicator to the onset of a failure condition. It will help you if you've got context because it's online. It'll help you determine the severity, and it will guide next steps. It's not a multi-gas. It's not going to tell you the exact fault. The normal next steps are to go and draw an oil sample, get it into the lab for dissolved gas analysis, and then based on the outcome of those devals, go and take this, pick the appropriate next action that you'll take. We spoke about what does a preventable transformer look like. I couldn't resist throwing these in. These are two examples of faults that if they'd have been caught earlier, there's a higher likelihood that they could have been saved before the fault got to the point where this winding could not be saved. These transformers weren't monitored, and at some point they've now gone to the point where the failure had gotten too bad, and I believe one of them tripped under short circuit. One of them, I don't remember the fault for the other. But this is what a transformer preventable fault looks like. And remember, we said up front is one failure that could be prevented, is one not too many. This is an example. I love this one. It's one of my favorites of a preventable fault that did get prevented. This particular transformer, they picked up the hydrogen as they energized and started to bring load on. They saw a lot of hydrogen production. They went in, they had a look, they found some arcing from their analysis, opened the transformer, drained it, inspected it, and found that particular bolt wasn't tightened down enough. And so the connection to the lug was bad. I cleaned it up, tightened it up, and that transformer went back into service. And that was a very expensive transformer. That was a GSU. You can only imagine how long and how expensive that failure would have been had it not been detected. So that's an example of a preventable failure. So I'm going to start summarizing a little bit for you. Why do you want to do online key gas monitoring as opposed to what we're doing today? The first thing is I say real time. It's near real time. It's actionable insight into the condition of a transformer fleet. We see online key gas monitors as part of fleet monitoring, not an instrument to determine the state of a single transformer. For that, a permanent installed multi-gas or a portable multi-gas would do the job. Online key gas monitors are really part of fleet monitoring. They're meant to be there perpetual. You'll save money on your business immediately. There's no question about it. The return on investment is compelling, and it is a self-funding. You just go back, and there's an IEEE standard that shows all the different ways you save money, but you just need to save one transformer to self-fund this project. If you're a utility, you can defer your CapEx, but regardless of whether you're a utility or a CNI, you're going to reduce your maintenance spend. You certainly will spend less on maintaining your products. We spoke earlier, hydrogen monitors are very, very cost effective. Remember, one of the biggest objections is that's too expensive. Well, yes, a large multi-gas is expensive, and it's kind of hard to justify putting it onto a smaller distribution or industrial transformer. But hydrogen monitors are very cost effective, and they can be installed on an entire fleet. And your time to value is immediate. On average, we take 1 to 2 hours to install it and start seeing data from them. There's no requirement for outages unless your standard work practice requires that. There's no long projects. Another thing is, if you look at the new NFPA standards, you are obliged to do monitoring. It's not necessarily online monitoring, but you are required to do it. You are required to keep records. And if you do have these, you're getting the added advantage of supporting your NFPA compliance, because the online monitors they are doing the monitoring, and they are doing record keeping for you at the end of the day. I always ask this question. Unfortunately, I can't ask the question and wait for you to answer, but I often ask the question, who's the most invested? Who is more invested in ensuring that a transformer continues to operate reliably than you? Normally get the CFO, the CEO, that person, the environmental health. No, the answer is your insurance company, the carrier of that insurance, the underwriter of that policy. They are deeply invested in seeing that. And one of the largest insurance companies wrote a standard for single and now more recently multi-gas to define what they felt a monitor should do in an effort to reduce the likelihood of failure of a transformer. Again, we can't prevent everything. We always look to what are the preventable failures, and they wrote a standard. It's an FM standard 6250, if I remember correctly. And if you have that if you've got a monitor with that certification, it's the right time to have a conversation with the underwriter about your premiums and or the deductible or what's in it for you to buy it, because you probably will get it. And then finally, I haven't had a lot of interest in it, but I continue to maintain, if every transformer failure averted will have a significant carbon emission reduction. And if you're an organization trying to reduce your carbon emissions, this is a benefit for you. So we commissioned an independent study of just how much carbon was emitted if a transformer fails and over the different sizes. If you see value in it, reach out to us. Let us share that information with you, because that is certainly a benefit to you. Now, I would be remiss if I didn't talk a little bit about why today's data is tomorrow's gold. In fact, one of my team members, he came up with a term, and I can't let it go, is data will be more valuable than oil. I just love it, so I put it in here. But today you're going to buy a monitor to know what's going on in the asset. You want to know about its condition, and that getting an alert will drive a fixed set of actions, perhaps something like go get a manual oil sample. But if you're buying the right monitors, you're going to be able to create and store digitized performance data. Remember, transformers are very rarely digitized. And that data is going to support tomorrow's AI training. So you now have these added advantages. You're going to increase your asset efficiency. You're going to increase resilience. You're going to minimize unplanned outages. You will have data interpretation. Not only are you going to have gas, you're going to have patterns. You're going to be able, that are going to come through the AI training, and they're going to tell you what they're going to provide work guidance. They're not going to say, you're not going to look up a standard operating procedure that says do A, B, C. Based on the information you get, you're going to get topical and relevant work guidance as to what to do. And for those of you today, you're probably in periodic maintenance, but you're going to move to condition maintenance, and you're ultimately going to move to predictive maintenance. And all that's going to come from the AI training and your AI processes. And AI is no good. You can have all the AI specialists in the world, but without a significant amount of data, you can't go anywhere. So not only from monitoring do you get today's monitoring solutions, you're also setting yourself up for the future. And I'm often heard to say, tomorrow's winners are the people who are collecting data today. So that's really the story. I mean, why do customers, a little word from our sponsors here, why do customers choose H2Scan? We are exclusively a hydrogen sensor company. We make hydrogen solutions out of our sensors for a wide range of applications: transformer monitoring, petrochem, hydrogen economy, electrolyzers, and so on. We've been at it for 22 years. We licensed our technology from Sandia, but we had to convert that to a product, and we had to convert that product into an enterprise. Our sensors don't wear out. There aren't components in it that'll wear out, that need replacing, that can't be adjusted. So just to put down money behind that claim, that sensing element carries a 10-year warranty, I think it'll last forever. I think it'll outlast the insects that will survive a nuclear holocaust, I'm told. And anybody who works with us, they're not getting serial number 1 or 2 or 100. We have 700 million continuous transformer hours of service just in transformers. And if you look at our business as a whole, we have 1.3 billion sensor hours. So it's a product that's well established. It's very mature, very reliable. But with 24 patents, we're a company that continuously innovates. That's our specialty, because it's all we do. And anybody who's working with us, why do you want to choose us? Because you can, not only are you going to buy something that's good for you today, good for your future, but you can truly expect something even better down the line.
Wonderful.
Griddscan 5000 and 6000 are key products that we sell. These are the pictures on the right. They're very small. I'm going to show you a couple of pictures in a minute. But in essence, they provide a very accurate temperature and hydrogen measurement, both in the oil phase, liquid phase. The larger model will also provide moisture. As you know, moisture is a key indicator for paper degradation, and pressure. Pressure, if you've got hermetically sealed transformers, or if you're monitoring hydrostatic pressure, you'll detect early leaks before the oil level indicator works. They're designed for a 10+ year life. It's much longer, but the lawyers like us to be very specific. The most important thing about this product's got auto calibration. You'll install it. It will auto calibrate itself every single day of its life, as long as it's operating and there's no moving parts, there's no consumables, and there's no need to ever calibrate it. It'll just operate. It's IO ready. It does have the FM approval that we spoke about, the FM insurance approval mark. They're compact, they're small, and as I said, they're energy. They can be installed on energized transformers. I thought I'm going to throw it in, and I'm running a little low on time, but I thought I'd show you what it looks like installed. Look for the yellow circle. I picked as many industrial type pictures. This is a cabinet mount transformer, and you can see the sensor mounted there at the back in the gas phase of a very small transformer. This particular transformer has some significant gassing, and they needed to know what they could do with it. The one on the right is installed at a semiconductor plant because the cost of an outage just is so astronomical. But you see, it's very straightforward. It's very simple. The one on the left, this is actually in a volt transformer, but it just shows how simple it is to install even in a volt transformer. This will be this particular volt won't get flooded, but it's very comfortable living in a flooded environment for extended periods of time. And on the right, you can see the larger brother installed on the drain valve. This just gets installed on a drain valve. You'll see the power and comms lead into in this particular case, this particular modem. It's a prototype modem, but you see how simple it is to install. 1 hour and you're up and running. And then finally, nobody buys a monitor. Nobody buys the sensor. The sensor is simply the tool that delivers to you meaningful information. So what it's really all about is how we deliver the data to you, transport the data, process the data, and present the data. To do that, people can comfortably use their own SCADA systems, their own Pi historians, their own asset management software, but we also have an option for people. You can use our IoT platform. It's very straightforward. It's very resilient. Your data is protected. It will push transformer alerts and fleet status to you as needed via text or email. But most importantly is that you have no burden on trying to manage, maintain, upgrade, and support software that is getting, by the way, increasingly complex. It's scalable, so you don't need to buy. You don't need to say, well, when do I need a new machine? When do I need to buy a new software? No, it scales with you as you grow. The data is transmitted over the public cellular networks, over private network in the future if necessary, but basically we stay off your IT network, we stay off your OT networks, so we keep everything simple. We don't expose your networks to cybersecurity breaches. And this particular modem also has an LV, so 450 volt power quality monitoring option, so that you can start looking for Harmonics 2. So if you have a connection point. So in summary, single gas monitoring is the leading indicator. It'll help you avoid preventable costly power outages, environmental cleanup charges. Most importantly, it increases personnel safety. It's extremely cost effective. You can go it's cost justified on a 1 MVA transformer, and it'll digitize your network. So if you own your transformers, if you operate somebody else's transformers for them or look after them or maintain them, ask us. Let us know how we can help you. And with that, I am done.
Awesome. So we are reaching the end of the hour. Thank you, Andre. And you have such a great narrating voice. I bet you could narrate books, and people would definitely pay you to do that. But we have a bunch of questions here that we probably won't have time to fully get to. So I'm going to say we're going to save these questions that have been asked, and we're going to make sure to reach out to you individually with answers. But we're also going to answer them here for anyone who still has time to stay on. Does that work for you, Andre?
That works for me, yeah. And I apologize for those people for those taking a little longer. But hey, we had a great story to tell.
So the first thing I'll share with everyone is that we are going to share the recording and the slides to everybody. So know that you'll be able to get that information if you need to leave, including the questions we're going to answer now. So I'm going to start with Jeff G here. He said that earlier you mentioned H2 increasing and H2 decreasing. Can you speak a little bit more about this behavior? He was under the impression that H2, once dissolved, remains dissolved into the oil until degassing.
Yes, H2, it does dissolve, but no, it doesn't stay in that condition permanently. A few things will affect it. First, it's highly mobile. So if you, for example, have a free breather transformer, or you have a transformer with the smallest of leaks, or you have transformers where hydrogen can find a way through, it will. So hydrogen is particularly mobile. So that's the first thing. You'll see on the one example, you saw it drop off and it fell to zero. We had to look at it and had a breather. And I think my opinion is the breather wasn't operating as well as it should have. And so we saw some hydrogen escape through there. The second thing that will affect it is temperature and pressure. If a transformer is pressurized and hot during the day, and then it cools off and the pressure drops, we'll also see some dissolved gas, some dissolved variations in it. But at the end of the day, if you take hydrogenated oil and you just leave it in a vial and you leave it open and you monitor it, that hydrogen will over time escape. It is just such a highly mobile element, and it will escape. So I hope I answered the question. That I understood it well and I answered it. If not, please feel free to reach out to me. My contact information is here.
Great. Michael asked a very interesting question. He says that he'd be interested in seeing a comparison of H2 scan results with actual DGA. How often do we see false positives?
We've never seen a false positive. One of the particular issues of our sensor that differentiates it, our technology is not cross-sensitive. Our sensor only reacts to hydrogen. You can throw any and every other gas at it, including helium and any other gas. Our sensors won't react to that. They'll only react to hydrogen. So I am not aware of any false positives, and we've had multiple pilots and instances where people have tested our product against a multi-gas, and we're consistently right on point with our measurements.
Great. So similar question. Philippe asks, is the values of H2 online monitoring comparable to typical DGA values? For example, if DGA presents 10 parts per million at a specific day, the average values of H2 online monitoring should be also near 10 parts per million?
Yes, it would. I'm assuming a few things. First, it assumes you take your samples from the same place at the same time. If you take one sample from the top and one sample from the bottom, you might see some variations, especially if your transformer hasn't reached equilibrium. So that's the first attribute of it. The second is, you've got to be above what we call our lower detection limit. So if you drop, if it's a very low limit, we will detect it, but I think anything below 5 ppm, we don't guarantee the accuracy. But if you're at 10 and you're taking the manual sample, and you're taking the sample from the same place at the same time, there's no reason to expect anything different. And the experience has shown us that it's not. That's why, in fact, our sensors have the optional bleed ports so that you can take the sample from exactly the same location.
I think you already know the answer to this question, but I'm going to ask it anyway. Steve asks, does the sensor circulate the oil?
No. Yeah. The sensor does not circulate the oil. The bigger model, where we have had a request and we are looking at whether we're going to put a pump on it, but it does not. Now, remember we spoke about monitoring. Speed is not critical for us. The most demanding, and I'm talking way out left field demanding, I think it took 32 hours to see hydrogen travel down a pipe of a few millimeters thick, the length of the transformer. But by and large, I remember what I said, hydrogen itself is very mobile. And if that's the only gas we're measuring, being very mobile, it's not necessary. It simply might take a little longer for the hydrogen to reach us, for us to get that steady state value, but we will get it. Our sensor's also directly connected into the oil. We aren't pulling oil out of the transformer to our sensor. We're putting our sensor right into the drain valve. So there is, to be honest with you, unless speed is critical, which in the monitoring world, it shouldn't be, because within a day or two, within 1 day, unless it's a very unique case, within 1 day, you certainly should start to see the steady state values of the reading.
Great. So now, Andre, I've got 3 final questions for you. I'm going to do them rapid fire. The first one is, what is the process and cost for going through initial installation? If someone, watched the webinar and said, okay, we'd like to look at installing H2 scan, what would be the next step for them? What would that look like?
I'm not sure I fully understood the question. I mean, what is the cost? So I think we're really just...
Yeah, like the process of going through initial installation of H2 scan.
So, I mean, at the end of the day, identify whether you're going to install it in oil or in the gas phase of the transformer, and identify the valves. Make sure that we know what size your valve is, and that you've got a place for us to install it. Ensure that There's the ability to get power out of the transformer monitoring box, decide how you're going to communicate the data. You order the right model, you walk up to the once you're ready, you walk up to the transformer, you screw in the sensor with its bleed port into the drain valve, you open the drain valve, you bleed the air, you connect the power, you connect the comms, and you're up and running. So sorry, that's a very, very quick answer, but it's a pretty straightforward, unless your operating standards make it more complicated.
And how hard is it to retrofit H2 scan into an existing system?
We do it perpetually. Usually takes us 1 to 2 hours on an average install, and that's exactly the process I just described.
Great. And third question is, if you need to operate H2 scan from a remote location, how does that process work?
So operate, you don't need to operate. I mean, if you want to be able to access the readings, that's really the question. So as I said, the product will talk Modbus RTU, it will talk DNP3. So that data can go into a number of places. It can go into your SCADA system, you can poll it. It can go into an asset performance management platform, Pi Historian, any of your enterprise applications, that if you want. And then within your enterprise, there'd be a mechanism for you to access and see the data. If you use our IoT solution, you will go to your closest Internet Explorer on your phone, your iPad, your PC. You'll log in anywhere in the world, as long as you have the rights, whatever rights you've been given, you'll be able to log in and access the information and see anything about any particular transformer. You'll go to the map view or the list view, click the sensor you want to look at. All the information that you need is available to you that way.
Awesome. So final question from Willie. He asked, can H2 concentration decrease after a fault if the fault stops? Can the H2 go away where we miss it?
It can. Again, it depends. It does depend on the nature of how much gas was generated, and it does depend on how freely your transformer is breathing. If you've got a crack in a weld, if you've got a breather that's not working well, or a faulty pressure relief device, eventually it will dissipate, especially if it's a low concentration. But on an average transformer, it certainly should be there. It certainly is likely to be there for a much longer duration. And in that duration, and I think, other small things would tend to increase would tend to replenish the hydrogen. But in the purest world, if the transformer is really sealed well, zero chance, it would take very long. And so the hydrogen would stay, but in the real world, the hydrogen would, if it's a very low level, you saw that one example of the case study, it leaked through what I consider a faulty breather or a crack or something, and it disappeared.